Welcome back. Let's do a simple example of rate adaptation, assuming that you have two constellation formats, and you can do, you have a channel with Rayleigh fading with an average SNR of 20 dB, so that's 100 in linear scale, and you have a target bit error rate of 10 to the minus 3. And this is the relation between the bit error rate and the SNR, but you can also read off directly that it's about 10 dB and 15 dB to use QPSK and 8 PSK. So please spend a few minutes to do this rate allocation problem and then get back to the video. So let's now solve the rate allocation problem. So the values of 10 dB correspond to 9.55, 15 dB is about 30 in linear scale. So then this leads to these three regions. We know also that our average SNR is 100. So let me try to draw this. We will have an exponential distribution, something like this, average value of 100, and then we have different regions, something like this, at 9.55 and 30, yes. And then we have a certain probability of being below 9.55, that's this first case, so that happens with 9% probability. We have a probability of being between 9.55 and 30. Okay, something is missing here. This should be between 1955 and 30. So that's this orange region. Sorry, there's a typo here. And this happens with 17%, so 17%, 9%. And then there's a probability of being more than 30, and this happens with 74%. Like this. Okay, so this should be probability of gamma in 9.55 and 30. Now, based on this, we can compute the average rate. So there are three cases. With 9% chance, we will send nothing, so 0 bits. 17% we send 2 bits because we use QPSK, and then 74% we use 3 bits. And this average then gives us an average of 2.56 bits per channel use. On the other hand, if we only did QPSK, then the average rate would be 1.82, right? Because there's still outages, and then all the remaining time we will use 2 bits, so this is less. And you could do the same exercise for 8 PSK, and you will also find that it's less than 2.56. Good, this concludes the first strategy. Now we go on to the second strategy, which is a strategy that doesn't make sense, but we will go through it to understand why it doesn't make sense. The second strategy is power adaptation without rate adaptation. So here we fix a constellation, QPSK. We have a certain average power that we can spend, and we want to adapt the power to maintain a constant signal-to-noise ratio. So what we want is that the signal-to-noise ratio at the receiver, here's the symbol error rate, for instance, is always this value, and this value corresponds to our target symbol error probability, like 10 to the minus 3. So we always want to maintain this value, sigma. We will figure out later what sigma should be. Now we recall that the SNR at the receiver without power control is gamma, right? If we do power control, then the SNR at the receiver will be given by this expression. Right, and when you plug in P of gamma equal to P bar, you find the original SNR without power control. In this expression, the P of gamma is called the power control. So P of gamma is how much power we give when the SNR is a value of gamma. And then by doing this, we obtain this SNR at the receiver side. Actually, let me spend some more time on this equation because maybe it's not so obvious where this comes from. So let's first do it without power control. Then we always use power P bar. We have a certain channel power G, then N0 times bandwidth is equal to the SNR. With power control, we will allocate a power P of gamma, which depends on the SNR, times G over N naught B. This is the SNR after power control. Now I can divide these two equations, then the N naught over B goes away, the G goes away, and then I end up exactly with this equation on the left. So this is how the SNR with power control is related to the SNR without power control. Good. Oof. So now a simple strategy, which is called strategy 1, is called channel inversion, to make sure that this SNR after power control is equal to sigma. So if this SNR after power control is equal to sigma, I can solve for P of gamma, and then this immediately leads me to this expression. The question is now, how should I choose sigma? I find sigma by using the fact that the average power is some fixed value. Okay, so I have these two relationships, and then from these two relationships I can solve for sigma. And then it turns out that sigma has this expression. So the inverse of sigma is the integral of this thing. And now this is problematic because if you solve this, for instance, for Rayleigh fading, this is actually plus infinity, right? Which means that sigma is equal to 0, which is minus infinity dB, which means that the only symbol error rate I can support is, well, basically 1. I cannot support any communication. You have a second strategy, which is called channel inversion with cutoff, which means that you only apply this inversion above some threshold. And then you will meet some non-zero SNR, and of course for some part of the time we'll have an outage. But basically this is a very poor strategy. This leads to kind of poor performance. And the reason is that you're limited by the worst channels. Right. In order to meet your target SNR, you need to put so much power on the worst channels that you have nothing to give to the good channels. So this is a poor strategy. Now, you could imagine that the combination of rate and power adaptation would not be much better, but it turns out to be much more powerful. So in this case, what we will do is we will use more power when the channel is good, and then also a larger consolation. And this leads to this technique that we will call water filling. Now, to understand water filling, unfortunately, we need to go through some math. This is a slide I took from the first lecture where we review the basics of convex optimization. We have a convex objective, convex inequality constraints, and linear equality constraints. For this kind of problem, we can write down the Lagrangian, which depends on the unknown, as well as these Lagrange multipliers, where this lambda should be greater or equal than 0. This is the definition of the Lagrangian. We then solve for x lambda mu by setting derivatives with respect to x mu equal to 0. And we put this additional constraint, which states that lambda times g should be equal to 0. And this provides us enough conditions to solve for x lambda mu. Typically, this solving is done numerically. But there exist certain problems for which there is a closed form solution, and our problem is one of them. This is an example that we actually did before, so I'm not going to go through that again. If you want to try this, you should try it yourself and then look at the solution of in lecture 1. Good. Now, when we did this course physically, we had this homework problem where the students were supposed to solve the following problem. We have convex functions, and we want to minimize a sum of convex functions subject to each of the variables being positive. And then there's these linear constraints. And then the solution of this must satisfy this, with this follows immediately from the convex optimization framework from the previous slide. And this is a general formulation, but we actually will specify it to this problem. So this problem is one we will solve. So we have a problem that involves minimizing a sum of something like rates with weights. So this you can interpret something like a rate. And this you can interpret as something like an SNR. Subject to some constraint on these x's, and all of these x's are non-negative. And these x's you can interpret as a power allocation. And now the nice thing is that the solution to this problem has a closed form expression. So the optimal x is given by this, so it's a maximum of 0, 1 over some value gamma c minus 1 over gamma k, where these are the gamma k's. And this value gamma c should be suitable to make sure that the constraint A transpose x is equal to minus b is met. So it is a good but challenging exercise to solve this optimization problem using what you learned here and see where you end up. So again, please pause the video, try it, and then you can come back.